Well, hello class. Tomorrow, or well, Tuesday, I am not going to be able to attend the class as I was sending out in an email. So I'm creating this video for the P material, and for the FM material. I have created a video previously and we'll link it, and we'll probably link another video if I can find one, or create one to go over the other material that you guys will need for the homework. And as I said in my previous email, this week we'll be finishing up pretty much all the material for exam P that you'll need to know. And for exam FM, we've already finished up pretty much all the material. This last video that I post should cover everything else. So for exam FM, I've posted about 30 questions. I'll give you guys longer time to finish it for this week's homework, and I'll do the same next week for P. And I've given you an extra day to do your homework for P just because of the holiday. So getting into our joint discrete function of random variables. So the mass function here, we know that our probability mass function for n independent random variables is equal to, for x of n is the random variable, we know that is each one is equal to the other. And in probability terms, that is just the intersection of each probability. And we know if they're independent and independent only, we can break these up and multiply all the terms together. Now, if they are not, we have to do some other things. And one of those other things we could do is the marginal probability mass function. If we can consider a subset of x1 to xn, for example, x1 only, the corresponding probability distribution is sometimes called the marginal distribution. Since the joint probability is the probability of intersection of sets, we add the joint probability mass function to compute the marginal probability mass function. For example, the marginal probability mass function of x1 is obtained by adding the joint probability mass function of x1 of x2 over all the possible values of x2. So f of x1 is equal to a1 is equal to probability x of x1 is equal to a1, or the sum over all possible a2 that the probability of x of 1 is equal to a1 and x of 2 is equal to a2. And if you had the continuous, that is when we would integrate and not just take the sum. And here's another example really quick. So problem types. Problem for this topic include the following types. Identify some constant for the probability mass function, which is useful formula for the probability. We know that the probability must sum to 1. And the joint, marginal, and conditional probability all related. We can go from one to other. So here's the conditional of x1 conditional on x2. That is the probability of x1 and x2 divided by the probability of x2. So this is just probability of x2, and this would be the joint. So that is the joint divided by the marginal. That is how we get the conditional. And we can, of course, compute moments. So let's compute the posterior definite distribution and the posterior mean from the given prior distribution. Let's consider the following problems. Suppose as x is distributed in binomial n comma p, and p has prior distribution with density pi of p. And then the joint likelihood is given by probability x is equal to k. P is an limit of gp. We know our distribution for this, just because we know it is binomial, is n choose k times p to the k, 1 minus p to the k, pi to the p, dp. And then the marginal, we have to integrate from 0 to 1 over our dp. And then so we'd get our conditional distribution is right here. And this is the likelihood function, or we could say the likelihood. And using the posterior density, one can compute the conditional expectations to posterior mean and posterior variance. So the expected value of p given x is equal to k, we integrate over to 0 to 1 of p. Probability p is an element of dp given x is equal to k. And the variance for the posterior variance of p given x is equal to k is the expected value of p squared given x is equal to k minus expected value of p given x equal to k quantity squared. So the same thing as our normal variance. And now here we'll be going over some examples. So the first example is an insurance contractor reimburses a family's automobile accident losses up to the maximum of 2 accidents per year. The joint probability deduction function of the number of accidents of a 3-person family home is given as this right here, where we have person X, Y, and Z. Those are our 3 different people, you could say, where X is 0 or 1, Y is 0, 1, or 2, and Z is equal to 0, 1, or 3. X, Y, and Z are the number of accidents incurred by X, Y, and Z respectively. To determine the expected number of unreimbursed accident losses given X is not involved in any accidents. So we know X is all going to be equal to 0. Now we want to figure out the expected number of unreimbursed accidents. And we know we get the first 2 accidents are reimbursed. So we have our 3 steps. Calculate the probability max function and make sure it sums to 1. So that means we have to figure out what our K is. In doing that, we get K is equal to 1/3. Now we need to compute the conditional probabilities when X is equal to 0. And then using that, we can go from that to calculate our expected value of our unreimbursed losses. So that means when our accidents are greater than 2. And from that, we get 7/9 is the expected number of accidents that are unreimbursed. And the maximum amount of unreimbursed losses we could have given X is equal to 0 would be 2. We look at this just because we know we get 2 as our maximum value of Y, and our maximum value of Z is 2, and we get 2 accidents paid for. So that would be the maximum total possible, but we're looking at the expected number. So example 2, let X and Y be discrete random variables with joint probability mass function 2x plus Y divided by 12. And we get the values for X and Y to our right here. So determine the marginal probability function of X. So that means we have to figure out what happens when X is 0 and when X is 1. What do we get for our Y value? So here, probability of X, we know that this is equal to 0. That's sum over all the Y's when X is equal to 0. So this is equal to, right here with the summation over Y1 of the probability X is equal to 0, comma, Y is equal to Y1, and that's all those possible ways. So that is how we got the probability for that. And the second one we would just do when X is equal to 1. And we can get that by plugging in our values here. And we know these are the 4 pairs we could possibly have. That is how we get the number here. Solution B when we sum them together. Now going on to example 3, we get our conditional table right here, which is always nice. That way we don't have to calculate this. Now let X and Y be discrete random variables with joint probability function given below. What is the variance of Y minus X? So that means we want to find the variance of Y and subtract the variance of X from it. So compute the marginal distribution of X and Y. That'd be our first step. So that means we want X alone and Y alone, or X minus Y. And we can get this here. So we can have X minus Y is equal to 0. And those are the cases right there. Plus the expected value of X minus Y is -3/5. And now for the variance, we know the expected value. We have our expected value. We can square this, but we also want the expected, this quantity squared to subtract it from. So we get the difference of that is once we do those both combined, we get that as 26 divided by 25th. And of course, it would be much easier to calculate it using it this way. But this way was pretty quick to calculate it anyways, as you guys can see. So either way works. Now example 4. A certain family health insurance policy covers up 2 claims per person per year during A certain family health insurance policy covers up to 2 claims per person during a year. In a certain family, there are 3 family members: a male, who is the father, a female, who is the mother, and a child. The joint probability function of the number of claims is this, as below. And we know this only covers up 2 claims per person. And we know the values can take up between 0 and 2. So we want to find the probability that the total number of claims for the entire family does not exceed 2, given that the adult male of the family, or the father, did not have any claims for that given year. So we would just do our same thing. We know that our x is going to be equal to 0. So then we have to calculate all our other probabilities. And given that x is equal to 0, we want to know that if that y and z together are less than 2, we can just sum over all the probabilities and then divide by the probability that x is equal to 0, which is using Bayes' rules, which we went over last week in depth. So that should be straightforward. Now I think this is our last example. Yes, so I'm going to pronounce this person's name wrong, so I apologize. So Mikko is performing a Bernoulli trial experiment with a probability of success p, where p is distributed over the interval 0, 1. According to the probability distribution with density of p is equal to 3p squared, for p is equal to 0 and 1, and otherwise it is equal to 0. As it is a Bernoulli, she performs the experiment 10 times and has 2 successes. Find the mean of the posterior probability density function p, i.e. p is given to 2, where x is the number of successful trials with Bernoulli success p. So if we go back up to our work up here, we know exactly how to calculate this. So if you're a little confused on this question, you could relook at our posterior distribution on page 2. But we'll go through the work anyways. So we want to find the expected value of p given x is equal to 2. So first we need to compute the joint probability function. So probability of x is equal to x, and p is an element of dp. Here's our function. And then of course we can move the 3 outside and add 2 to our x once we distribute this. Because we distribute this, the 3 can go out front and put the 2p here, so make that x plus 2. And the conditional probability of the posterior is beta, with x plus 3 counted 10 minus x plus 1, when x is equal to 2. So that we should have. I believe we covered, or I posted notes on beta earlier, where beta here is the function of beta is right there. And then using our we could use our beta function, but we could just find the probability of p. So that means we know p goes from 0 to 1. So we'd integrate over 0 to 1. Add our p in here to find the expected value of p. And it is not x in this case scenario because we are given that x is equal to 2. And we are looking for p, not x, which is why we're adding the p here. Then we multiply it by our probability function for our posterior. Or, well, this is just our posterior distribution right here. So here is our posterior distribution. And this p right here is not x, just because we know what our value of x is. And we're looking for our value, and we're looking for what p will be, or the expected value of p, not x. And from that, we could see once we multiply the p up to the top, that this becomes 6 minus 1. And this is 9 minus 1. And then using our variance function for beta here, our expected value for beta, this is now in our beta form. And this is beta 6 comma 9. And then we know that this is just 5/4. Whoops, there we go, 5/4. So that is how we would calculate that one. And that would give us answer, 5/14, which is answer E. And I believe that is all. So if you have any questions, please let me know, post on Slack, or show up to office hours Wednesday, as I should be there. Otherwise, it is great talking, and I will see you soon.